So in the last video, we developed the definition of the derivative. So now let's look at some examples where we use the definition of the derivative to find the derivative of a function. So let's start with this one. If f of x equals 4 minus 2/3 x, use the definition of the derivative to find f prime of x. So the definition, again, f prime of x equals the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Alright, so again, f of x we have right there. We're just going to put in this 4 minus 2/3 x into this limit. But when we look at f of x plus delta x, well, what we need to do is take our function, and anywhere there's an x, put in an x plus delta x. So this is going to end up being 4 minus 2/3 times x plus delta x. Alright, so let's put everything into our limit. So we're going to have the limit as delta x approaches 0 of 4 minus 2/3 times x plus delta x minus f of x, so that is 4 minus 2/3 x, all over delta x. So we took our f of x plus delta x, which is this, substituted it into our limit. We took f of x, which was this, and substituted it into our limit. Now we need to evaluate this limit. So we're going to end up with the limit as delta x approaches 0. Alright, so let's kind of distribute things. We have 4 minus 2/3 x minus 2/3 delta x minus 4 plus 2/3 x all over delta x. Well, it looks like some good things start happening. The 4's cancel out. The 2/3 x's cancel out. So we end up with the limit as delta x approaches 0 of a negative 2/3 x, or 2/3 delta x, sorry, all over delta x. All these delta x's cancel out, and so we end up with the limit as delta x approaches 0 of a negative 2/3. So now we put in 0 for delta x, which there is no delta x, so we get a negative 2/3. And so when we start off with f of x equals 4 minus 2/3 x, f prime of x equals a negative 2/3. Now, this one was just a I guess just kind of make a point here. Notice that this is the equation of a line. Right? So this is an equation of a line. So if I were to sketch out this equation of a line, really quick sketch here, we would go up 4, and we would have a slope of a negative 2/3. So you'd go down 2 and over 3. So it would look something like that. So the slope of this line is a negative 2/3. And if the derivative helps us find the slope, then it makes sense that the derivative is a negative 2/3, because no matter what value of x I put in, the slope of the tangent line would be negative 2/3. Actually, in this case, the tangent line would be the line no matter where you are. So it just kind of shows that this definition of the derivative does work even with something as simple as a line. Let's try another example, one that might not be as straightforward. If f of x equals the square root of x, use the definition of the derivative to find f prime of x. Okay, so let's go through the same process. We know that f prime of x equals the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. So this time I'm just going to put this equation straight into my limit. So we're going to go the limit as delta x approaches 0. Okay, so f of x plus delta x, so we take x plus delta x and put it into the square root of x. So that is going to be the square root of x plus delta x minus the square root of x all over delta x. Okay, so we need to evaluate this limit. Now in this case, we don't have any way to distribute and see if things cancel out. But back when we studied limits, we did have a technique that works very well for this. And that was to create and then cancel a common factor. Now in order to create and then cancel a common factor, we're going to have to multiply this by the conjugate. Alright, so I'm not going to have room here, so I'm going to rewrite it. We're going to have the limit as delta x approaches 0 of the square root of x plus delta x minus the square root of x all over delta x. And we're going to multiply the numerator and the denominator by the conjugate of the numerator. So we're going to have the square root of x plus delta x plus the square root of x all over the square root of x plus delta x plus the square root of x. Alright, so let's see what we have left. I'm actually going to go down here. This does get a little big. So we get the limit as delta x approaches 0. Alright, so this is these are two big binomials. So we have this times this becomes the square root of x plus delta x squared. This times this becomes plus the square root of x times the square root of x plus delta x. This times this becomes minus the square root of x times the square root of x plus delta x. And then this times this becomes a minus square root of x squared. And this is all over delta x times, and I'm just going to not distribute that. So we have x plus delta x plus the square root of x. I think some good things start happening here. These two, so this is just a plus square root of x times the square root of x plus delta x, and a minus square root of x times the square root of x plus delta x. So these cancel out. That's good. And so we're going to end up with the limit as delta x approaches 0. Alright, now that gets squared, so we get x plus delta x. That gets squared, so we get minus x all over this whole thing. So delta x times the square root of x plus delta x plus the square root of x. So let's see. Another good thing happens. These two x's cancel out, so they're gone. So we're going to end up with the limit as delta x approaches 0 of delta x all over delta x times the square root of x plus delta x plus the square root of x. And another good thing happens. These delta x's cancel out. So now we have the limit as delta x approaches 0 of 1 all over the square root of x plus delta x plus the square root of x. Alright, so now that we've gotten this delta x out of here, we can now substitute in 0 because we don't have that issue of dividing by 0. So we're going to get 1 over the square root of x plus 0 plus the square root of x, which ends up being 1 over 2 times the square root of x. And so there's our answer. So if f of x equals the square root of x, then f prime of x equals 1 over 2 times the square root of x.